my question to you is, would it work out to be like this? In antiderivative of this times antiderivative of this. Would it work? No, of course not. Don't you wish your life is that easy and simple? See, when we are doing the product rule, that didn't work out because it was this, right? So if the differentiation did not work out that easy, why the heck in the world that antiderivative will work out nicely? You know what I'm saying? There's no way in hell. So that ain't gonna work. So then how do we figure this thing out? Well, we can study this chain rule, I mean the product rule again, in order to get an idea. So this technique called the integration by part is really reverse product rule. Remember, U substitution was reverse chain rule. So this is a reverse backward product rule. Think like that, something times something. It doesn't always work, but I'll tell you when this thing works. But let's review this first. So if you are differentiating this thingy, and then you have x sine x. Now let me remind you of what this thingy was. This thing is u prime v plus u v prime, isn't it? So we'll just follow that product rule, and then u prime 1 and v, so we have sine x plus u, which is 1, and v prime, which is cosine of x. So far so good. Now what I really want to know is what the antiderivative of this thingy is, right? This is the guy that I want to concentrate on. So why don't I take an antiderivative on both sides of this equation? Antiderivative of this is easy. You just erase this derivative symbol now, isn't it? Space, watch for the space. So what I have is x sine of x is equal to this. I know what the antiderivative of that is, but in order to figure out the procedure or the formula, let's write it like this, sine x dx, and then plus, this is our guy, x cosine x dx. Once you write it like that, remember we are trying to figure out what this is. This is the integral antiderivative of something times something which we don't know how to do, which this we know what to do. This, of course, is already figured out. You see how nice that is? So let's solve for this thingy now. So what we have is antiderivative of x cosine x dx is equal to x sine x minus, because we are rearranging it to the other side, and then sine x dx. So far with me? Now we can finish this off by saying x sine x and minus cosine x, but if I differentiate this, I pick up negative sign, so that better be positive. Are we good? Now, it's easy to say like that because we already knew where this thing started with, right? But you're probably asking, how can we figure that out without knowing what this is then? So we need a system, more systematic approach. So let's figure out that formula, okay? So if I take an antiderivative of this red ink right there, then what we have is this is uv, you know what I'm saying? The x is u and sine x is v, and that is equal to, this is of course integral of, let me write it a little differently, v first, du dx dx, okay? Plus, and this thing is of course u dv dx dx. You with me? Okay, now, so I'm trying to figure out what that is. Now here we abbreviate u dv as if we cancel that x just to make the formula looking nice. It really didn't cancel. This is really it, cosine x and dx right there, right? But this just for the simplicity of the formula's sake. Most books are abbreviated like that. And then this uv here, u times v, which is u times v, and then minus the integral of minus, and then this part, v du. This is the integration by part formula, if you will. Okay, Oh, that didn't work out. Let's try that again. How come this thing gives me trapezoid instead of rectangle? Okay, now it's a nice rectangle. Okay, now let's try this in more systematic way then. Okay, so we'll start this thing over, creating more space here. So now we have x cosine of x dx. So this integration by part works if you have something times something, and when you can differentiate one and integrate the other one. Now, in doing so, whatever you're differentiating must get simpler, and whatever you're integrating does not mess up a whole lot. This is the only time this works. It doesn't always work, okay? Now, so u is always the simpler one, well, most of the time, simpler one, x, and then dv is the other one. Remember, it was cosine x dx. So far, so good? Now you differentiate one, which gives you dx, which really means du over dx is equal to 1. And then you integrate the other one, and this gives you sine of x. So far, so good? Now this whole thingy then becomes, remember, uv from the formula, but its process is easier to remember than the product. This minus this, you get it? uv minus v du. This, so I want you to write it in exactly this format on this side, this column. So you can do this minus this. You get it? Boom. So we have x sine of x minus comes from the formula because we rearranged this line, and then these two. You follow? Now, then we can finish this off. So this is x sine of x minus, well, becomes plus cosine of x plus c. How about that? So far, so good. Now, somebody in third period asked me, how come we don't put plus c here, right? Well, that kind of messes up a lot, because then when we do this, then there's a plus c here. That's least of the headache. And then if we do this part, there's a plus c mixed up, and we have to integrate that. That's not really the point. The whole point is, whenever you find the antiderivative, these are families of curves. They only differ by constant. It could be any vertical shift, right? So we only need to add it right here. I'm not sure if that's good enough answer, but so we don't put it right there, okay? Now, let's do another one then. For real, now we don't know where this thing came from. So if we have x squared cosine of x dx. Now, space, lots of vast amount of space. U, of course, is x squared, and dv is equal to cosine of x dxa. So far, so good? You follow the procedure? Now, then you differentiate one, du, du is equal to, now this time 2x dx, good, and we integrate the other one, so this becomes sine of x, good. Now, so it's this minus this, like that, so this thingy now becomes x squared sine of x minus the integral, minus sign, and integral comes from the formula, and then these two, 2x sine of x dx. With me so far? Well then, this is not over. We still have something times something now, don't we? So what should we do now? Round 2, right? We do that all over again. U, now this time. Now, here's a dilemma. Here's a minus sign. Here's a 2. Should I take that outside and then bracket and then distribute later? No, don't. It gives you the same answer, but from experience, I know if I just throw it everything here, like that, on a u side, it'll distribute itself for you. You can check both ways, but this is less writing. This is a lot of writing already, so I want to minimize the writing, okay? So sine as well as constant goes on the u side always. And then dv here is then sine x dx. Don't forget that dx. Now you differentiate one, so du is equal to -2 dx, and integrate the other one. So this is cosine of x. Wait, no, negative. You get it? Are you with me? Now, and here's a correct grammar. This x squared sine x is already there. So you have to recopy it. Don't worry about the sign because they're all here. So this minus this. So uv, you have a negative sign here, negative sign here, negative sign here. So it all becomes positive and negative. So we have minus integral of, oh no, not the minus integral of. Let me start over. uv, minus sign here, so it becomes positive. I was right the first time. And then you have 2x cosine of x, then minus the integral of, good, because it was uv minus integral of these two. Now I have a minus sign, minus sign, minus sign. This remains as a minus, and then we have 2, and then cosine of x dx. You with me? Now, in your book, they have something called tabular integration. If you look at the Dropbox note, I said, don't even read that section. It's something stupid, okay? I got a degree in math without knowing what that is. It's essentially this, but they make on it, it's not worth it. You're prone to make mistakes, so don't even read it, okay? I don't want to see it. Just this is good, okay? Now, then we know how to finish it. X squared sine x plus 2x cosine of x, and then antiderivative, that is sine of x, and don't forget to attach c right there. Good? Any question? One last thing.
Yes.
Yes, question?
So I'm just wondering, how do you get, I know you get u just from x squared, how do you get v? Like, how are you supposed to determine v?
Oh, it's whatever's left is your v, dv. So if you call this thing to be u, then whatever's left is dv.
Oh, so you just do the, okay.
Yeah, so it's this integral is something times something else. So one is a u and the other is v. You get it?
Oh, but I thought on the right side you write v as sine x, not cos.
Oh, okay. It's really dv. U, this is u dv. So you differentiate one and you integrate the other. How's that? That's where the sine x, the v comes from, the antiderivative of this thing. Like I said earlier, this integration by parts technique is when you can differentiate one and anti-differentiate the other one. That's the only time this works. And even then it's a maybe. It doesn't always work. Okay? Now, last thing, cosmetics. I call this u and I call this u. That's inconsistent. You cannot do that in the same problem in math. So subscripts 1, 1, 1, 1, and then 2, 2, 2, 2. Now it's perfect. But don't be concerned with these subscripts in the middle of the heat of the moment, because they drive you crazy. Just put it at the end. Good. Let's take another example. This one. Now this one, well, if you have x and then ln x dx, what you want to do is, of course, u is equal to x now, right? Because that's easier, simpler. And then dv is equal to ln x, eh? So we differentiate one, du is equal to dx. Oh, that's very nice. It got simpler. V, whoops, here's where we run into problem. Does anybody know what the antiderivative of ln x is? You know what I'm saying? So this is where we get stuck. So this problem will force us to go the other way. So we scrap this idea. So only thing we know how to do with ln x is this. Differentiate it, right? Then we get 1 over x dx. Get it? Now this thingy, wow, what is this? What is dx? It's 1, you know what I'm saying? And then if you find the antiderivative is x, so it didn't get prettier. It got a little bit uglier, but hopefully this is minor thing. We'll see. uv, and then, oh, by the way, don't be writing it like that, like that. You see what the problem is if you write it like that, right? So no, don't do that. Let's write it like this. uv and minus integral of this, okay? But these two, hallelujah, x is cancelled, eh? It's just this, isn't it? So that wasn't bad. You get it? Some of you look puzzled. Question? Is this minus integral of this?
Yes, I have a question. So I saw the u is ln x, and then dv should be everything left, which should be x dx, should it?
Oh my God, that is a nice catch. This is x dx. Yes, thank you so much. You saved me quite a bit. So this should be x squared over 2 then, eh? Let's start over. So uv, which is x squared over 2 ln x. Wow, your nice catch will live forever in this video. Okay, for the record, her name was Echo. So let this name be remembered forever.
Extra credit?
Don't push it. So this, but everybody will remember your name forever and ever, as long as this video lives. And then now minus the integral of these two. Oh, one of the x cancels, so this is x over 2 dx. Okay, that's a little bit uglier, but not that ugly. Still, one of the x cancels. Good? Okay, because we still know how to find the antiderivative of this thingy. See, this part, uv part is done. You don't have to find the antiderivative. That's the nice trick. And this thing is minus then x squared over 4 plus c. How about that? You get it? Are you with me? Okay then. Okay, so that's very nice. Now, well then, question before I move on to the next one? Okay, we're good, right? Okay, let's move on then. How are we doing in time? Whoops, did not want to do that. Oh, I did it again. I'll just do it like this. I want to move this thing. Why wouldn't you move? Really? It's okay. Okay, now, oh no, we do have to find the antiderivative of ln x now. Uh-oh. Now, let's decide what is u and what is dv. Well, this has to be this, right? Only thing you know how to do. There's only one term. And then derivative of this, of course, is 1 over x dx. Well, then what's dv? It's 1, you get it? It's dx. And then antiderivative 1, of course, is x, right? I got this big problem mixed up with the previous one. Now, you with me? Some of you look puzzled. Okay, so it's this minus this. So x ln x minus the integral of then these two. And yeah, this is what I wanted to do earlier. X is cancelled, so this is just dx. So x ln x and minus x. You get it? That was nice. Would that work like that? Let's check. I want to check. The way you check is you take a derivative of x ln x. Oh, almost forgot. God, no, plus c. Whew, that was close. Did I? Oh yeah, I have plus c on the previous one. X ln x minus, wrong color, minus x plus c. Will it work out and give us ln x? You see all kinds of mistake today. Once you start the day with a technical difficulty, this happens. Okay, let's see. This is a product rule because this whole integration by part, this backward product rule. You know what I'm saying? So u prime 1 times v plus u and dv. Good. And then this thingy is -1, and this thingy becomes 0. You see, this is 1 minus 1, they expect. So this is really product rule. You get it? Okay, then how are we doing in time? How many minutes?
6.
6. Okay, you can just quietly leave whenever you have to leave. I'm gonna finish this off for the sake of video. Okay, this is you, which is which in this case? I'm gonna rearrange it a little bit. There's a reason for it. So I'm gonna write this one first, then e to the negative 2x, and then dx like that. Okay, see, we can differentiate this. It doesn't get that much prettier, but we could, and we can integrate this. Or we can differentiate this, and we can integrate this. It can go either way in this case, right? Because one does not necessarily get prettier, so it's about the same thing. So my question to you is, which way is easier? Is it easier to differentiate sine of negative 3x or integrate anti-differentiate sine of 3x? There's a minus sign. You know what I'm saying with that? That's headache, isn't it? So there's more potential mistake to be made that way. Derivative of e to the something is still e to the something, which means anti-derivative is this. So this is easier to integrate. You know what I'm saying? So, and then space, see how much space I leave here. So u is sine negative 3x, and then dv is e to the negative 2x dx is how I want to do it. So far so good? Okay, so I differentiate this one. So this is going to be cosine negative 3x, and then chain rule. Good. And v is e to the negative 2x and reverse chain rule. Like that, eh? You with me? Now watch. uv. I'm gonna take this constant out to the front, so negative 1/2, and then sine negative 3x, then e to the negative 2x. Good. Okay. And then minus the integral of, and then these two. So I have a minus sign here, minus sign here, minus sign here. So it's negative. I'm going to consolidate all of the constants and put 3/2 here. And cosine of negative 3x, and then e to the negative 2x dx. How are we doing? Are we good? Okay. Now, round 2, right? We have to go to round 2.
Mr. Kim.
Yes.
I think you forgot to put the. Oh wait, never mind.
Never mind. Okay. Oh, okay. Alrighty. Now we have to decide for the round 2. So before I forget, subscripts 1, 1, 1, 1. Which is u and which is v now?
Mr. Kim, actually, I think I realized what she was going to tell you.
The x after the du.
The du.
Oh my God, that's a nice catch. dx. Okay, that's a minor fix. Amazingly, if you forget to write dx, then I never forget to deduct a point to remind you. But I forget myself all the time, and I still don't know how that works out like that. It's one of those amazing things that I sometimes amaze myself. Okay. Which is u and which is v now? This is a very common mistake, so I'm gonna screw up for you intentionally. This is going to blow up, so don't write down whatever I'm about to do, but this is kind of amusing. Some students do this. I want to switch now and say, this is my u, so I'll do negative 3/2 e to the negative 2x is my u. And then some of you already see where this is going. dv is then cosine negative 3x dx. Good? Well, no, not good, but we'll see what happens if you do such a thing. And then du will be derivative. So this is e to the negative 2x. Chain rule cancels that and gives you this, which is nice, right? Very nice. I know it's very nice. And then V is this becomes sine negative 3x, and then reverse chain rule 1/3, right? So let's watch what happens. This is already there. Negative 3x e to the negative 2x. So far so good. And then we have uv. So minus these two. So 3's cancel. Isn't that nice? And we have a positive, and we have 1/2. And then we have e to the negative 2x sine negative 3x. So far so good. And yes, Matthew.
I'm pretty sure it's actually a negative. Or was this?
Yes, it is. Because there's a minus sign from the, this is just UV part. So this is negative, then this is negative. So it's positive.
But what about the upper thing was minus? Is it just a
no, that minus sign, I gave it here. So I'm distributing already.
Oh.
Instead of having it outside and bracket in order to save writing. Get it? I mean, besides, this problem will blow up anyway, so watch what happens. You notice that these two cancel already, which is very nice, right? Yeah, I mean, okay, that's great. And these two, 3's cancel, right? And then let's figure out the sign. This is minus sign here. There's a minus sign here, so this becomes plus. And 3's cancel, so you have e to the negative 2x, and then sine of negative 3x dx. And then these two got cancelled, right? Now you're thinking, why does it look so familiar? You see that this is exactly what we started with. Remember when you're doing proving trig identity last year, and then you, without looking at where you're supposed to go, you just keep working, and half a page later, wait a minute, that thing looks really, really familiar. And then you look up and that's the problem you started with. Yeah, it's kind of like that. So learn from this mistake. This happens because here I switch these two. See, when I said dv is e to the negative 2 and then trig function is u, then I have to stay with it. If you go back, then you're going back to whatever you started with. Okay? So it blows up like this. So let's not do that. I'm gonna redo the whole thing now. So here, I'm gonna get rid of this part. And let's do it the correct way. So this is already there from the top, and it's just this part I need to do. So my u should be 3/2, negative 3/2, cosine negative 3x dx. Oh, not dx, that. And my dv here is equal to e to the negative 2x dx. So far so good. Now then differentiate one, so du, this becomes positive. Good. Cosine, derivative cosine is negative, so it becomes positive. So sine and then negative 3x, but the chain rule brings the negative sign back, so this becomes negative 9/2. You with me? Who's confused? You with me?
Mr. Kim.
Yeah.
I'm just wondering, does the negative 3/2 has to go on u, or it can go on dv too?
Yeah, it can go the other side too.
Okay.
Yeah, it can go to dv as well. It's just like, only reason I usually put it on this u side is differentiation is easier than integration, because that backward chain rule, sometimes you want to cancel. No, it doesn't cancel. So that's why it's my habit to put it, but you could actually put it the other side or like one of each, whatever. Okay. And then dx here, and then v here is same thing as before, e to the negative 2x, and then backward chain rule, so negative 1/2. You with me now? Okay, let's put this thing together. So this thing I copied from the previous line. Now I have uv here. So this is minus now, right? This too. So I have 3/4a. No, not the minus. Here's the minus sign. Here's the minus sign. So I have a plus 3/4. And then I will have cosine negative 3x. And then e to the negative 2x minus the integral. Good. Now you realize why that I left that vast amount of space here. And then these two. Okay, so I have a minus sign, minus sign, minus sign. So it stays minus. Constant wise, 9/2, 1/2. So this is 9/4. Good. But this time, actually, you don't have to, but I'll just write it like that. Then these two. So we have sine of negative 3x and in e to the negative 2x dx. You with me? Then you're saying, wait, isn't that the same thing? Didn't we go back to exactly what we started with? And then, oh, subscripts. Where does it end? Because this will go on forever, indefinitely. You know what I'm saying? Ah, this is a dilemma, but, you see there's a minus sign here, then this is plus, so they don't need, it's not exactly the same thing as that there's a constant. Here's thingy. Let's just look at it. This whole thingy is equal to this whole thingy. Actually, I can do copy and paste. See, one nice thing about distance learning is I can do copy and paste. So copy, and I'm gonna put it here. Because I want you to take a look at this situation. Which this line you don't have to write it like that. I just want to make a point here. This is what we have, correct? Heck, I'm gonna put different color to emphasize this point. I'm gonna put red. Can I move this thing over to the other side? Because this is 1 right here, this is 1, and this is 9/4, so I add to the other side. What's 1 plus 9/4? Is it 13/4?
Yes.
And then this integral of sine negative 3x e to the negative 2x dx is equal to negative 1/2 sine negative 3x e to the negative 2x plus 3/4 cosine negative 3x and e to the negative 2x. What just happened here? We figured out what this integral is equal to. Ah, okay, let's not forget c. Whoa! All we have to do is multiply both sides by 4/13, eh? Dang, huh? Let's do that. We can write another line, or we can just take an eraser out. You can just take an eraser out and fix it, but hey, this is a computer, right? So I actually can do this. There you go. So all I have to do is multiply both sides by 4/13. Good. So this thing times 4/13. So it becomes 2/13 like that, eh? Good. This thing times 4/13. So does this become 3/13 then? Are you with me? And then, of course, this is like 4/13c, but we can call that different constant. Oh, that looks like derivative. D, how's that? Ah, there you have it. We are done. And if you really want to make it pretty, you can common factor these things. I mean, you don't have to, but while we are at it, we can say e to the negative 2x/13, and then we'll have bracket to make it look while we are at making it prettier. So we have -2 sine of negative 3x, and then plus 3 cosine of negative 3x. Beauty, eh?
Okay.
Yes.
I'm just wondering, like, why don't you use an even and odd trick, like, throughout the problem? Like, could you technically not factor out the negative? Yeah, kind of factor out, get a negative out of the sign.
Yeah, sure.
Okay.
You can do it.
Okay.
You can even switch these two. It's just preference. Whichever looks pretty to you, you can do it. I mean, you can leave it this way, and I'll take it.
Okay, so like we can simplify it more, right?
No, this is as pretty as it's gonna get now.
Okay.
You get it? You kind of get it, but you don't at the same time. I mean, this I threw a lot at you.
Yeah, I mean, like at the last line, you can get all the negative sign out. Could you technically?
Yeah, you could.
Or that's not kind of.
You can put negative here, so this becomes positive. This becomes negative.
No, I mean the even odd trick identity. So that's -2 sign. That's what I'm.
Oh yeah, that. Oh, you can do that too. Well, actually, yeah. You can definitely do that. Actually, we could have started that way. This is what Josh is saying, right? Like that, odd function. And this is an even function, so it's still this. You can even do this if you want to. You don't have to. You can just stop right here, okay? Because on the test, cosmetics is not as important. You just want mathematically correct answer and move on to fry the bigger fish. You get it? Okay, any question? Okay, differential equation. So we just integrate, so this becomes y is equal to integral of theta and then inverse secant of theta, d theta. You know what I'm saying? Oh, that d is ugly. Now it's something times something inside the integral. So we want to do integration by parts, right? So which one is u and which one is dv? Your first instinct is you, of course, want it to be theta, and dv should be then inverse secant of theta. You know what I'm saying? So that's nice. U is equal to 1, d theta, and then v is equal to, whoops, we get stuck. Does anybody know how to integrate inverse secant of theta? I mean, there's a way, but that itself takes the integration by part. So it's like, yo, we are defeating the purpose here. You know what I'm saying? So much for that idea. So we scrap this plan. I know you wrote it already. I know. Hate me when I do this, but I have to show you how things can blow up. So we'll say u is equal to, and hopefully you remember how to differentiate this thing from chapter 3. I'm going to show you. dv is equal to theta, and then du is equal to u. Let's do it on a side here, okay? Whenever I switch to green ink, it's like, remember from the past, recollection. That thing is, say u is equal to inverse secant theta is same thing as saying secant theta is equal to secant u. My God. Secant u is equal to theta. You know what I'm saying? And then this is misleading because theta is usually an angle. No, in this case, u is your angle, right? Then we can differentiate implicitly on both sides. So this becomes secant u tangent u. Du over the theta. You know what I'm saying? And the other side becomes 1. You remember forgetting this? Chapter 3. Then du over the theta is secant u. This is already theta here, okay? So we can divide. So what we have is cotangent u over theta. Very good. Now we have to figure out what cotangent u is. Okay, so for that we draw a diagram. Now we know better not to put u up here. I mean the data up here, right? As we did it this way, and then this u is the angle. Then we have to worry about, can u be negative? Can data be on the other side, second quadrant? You know what I'm saying? But our problem was nice enough to say, nope, data is positive. So there's only this case. In that case, you can actually put data up here too, but I just do it this way. Okay, this is 1. So this side right here is square root of 1 minus 1 over data squared, isn't it? And that is equal to square root of data squared minus 1 over data squared. And that is square root of data squared minus 1 over absolute value of data usually, but our data is positive. You get it? Now we continue here. Cotangent. Cotangent is this over that, isn't it? So we say 1 over data, this over that. So we flip it over and multiply, eh? So we have data over square root of data squared minus 1. But then I had this thingy here already. So square that. You get it? I usually had absolute value here, but we don't need that absolute value in this case. So this whole thingy turns out to be 1 over data square root of data squared minus 1 is what that du over the data is. Good? I know, huh? What a mess. Come back to the present time. It's like in the movies. You start, main character starts recollecting, and then like scene changes, and then oh yeah, that, and it comes back. Oh yeah. Okay, then du over the data is this. Good? So we have 1 over data square root of data squared minus 1. And let's put the data right there. Okay, and v is just data squared over 2, isn't it? Fully come back to our original problem now. So this thingy is equal to uv, this and this. So we have data squared over 2 inverse secant of data minus the integral of these two. Okay. Oh, one of the data cancels, so that's nice. So we have data over 2 square root of data squared minus 1 d theta. You with me? Are you with me? Okay then. So next line, data squared over 2 inverse secant of data. Now, we still don't know how to integrate this. But do you see u and du? This is u and that's du, derivative something and the derivative of that something. Because having two terms here is ugly, isn't it? So yeah, you wish there's only one term. So this time we do u sub, except I already used u here, so we use w sub. You get it? W. For some reason, it's not funny to the kids anymore. It used to be really funny previous years. W is equal to data squared minus 1 now. Good. And then dw is equal to 2 theta d theta. Are we good? So this part becomes minus. Now let's think. This is u to the 1/2 power, and theta d theta is here, so you divide by 2. So you have a factor of 1/2. And then there's that. So we should have 1/4, say. And then u to the negative 1/2 power du. Do you agree? Who's confused? Okay then. Moving on. So we have theta squared over 2 inverse secant minus, and this thing is u to the 1/2 power. Good. So you have to multiply that reciprocal, so therefore this thing becomes 1/2 plus
Wait,
c.
should it be W instead of U?
Yes. See, it is funny. Of course, it's double u. Why would you want to have a single when you can have double? Ah, yes, double u. Good.
You can't hear us laughing because we're on muted.
Oh, I see. So it is still funny, huh? Okay, good. Oh yeah, unmute laugh. No, that's asking for too much. It's like you're not the live audience of some sitcom, so hey, it's okay. Okay, now we have to bring W back. What the hell was W? So we have theta squared over 2 inverse secant of theta minus 1/2, and W is this thingy, theta squared minus 1 with a square root, 1/2 power, so theta squared minus 1. Oh my God, that was hideous, wasn't it? Yep. And then that is still being nice because they gave us this condition, theta is positive. If they didn't give us this, then you have to have case 1, case 2 is a whole lot of mess. Good. Okay, well then, average value. You remember mean value theorem? Part 2? You find the total area and divide by the length of that interval? Yeah, it's kind of like that, and they give you the interval, so this is what we divide by. Okay. So we just need an average value of this function. So let's do it. So average of y is equal to integral from 0 to 2 pi of 2 e to the negative t cosine t dt. And then you divide that by over 2 pi, which I will just put like that. Okay? Say yes. Okay then. Well, at least this thing you cancel. So 1 over pi, 0 to 2 pi of e to the negative t cosine t dt. Now, if you want to do integration by part with these things, that's gonna drive you insane. So I like to do this integral part on this column separately and then bring that result back, okay? So let me switch the color and work on that part. So this integral, e to the negative t and cosine t dt. Now we have to decide which is u and which is v. This is like about the same thing, judgment call. Do you want u to be e to the negative t or cosine t? Because there's a negative sign here, otherwise this is usually v. But this trick, it's like whoever the owner of this question decide. Which way do you want to see it?
U as an e to the negative t.
U is e to the negative t, then dv is equal to cosine t dt, like that, right? So you differentiate one, so you get negative e to the negative t. I'm gonna scroll, and then dt, and then v is now sine t, positive, right? And this is a little trade-off. Integration of trig function is the other way. Okay, so this thingy is equal to uv. So you have e to the negative t sine t minus the integral of these two. And here's a minus sign, and here's a minus sign, so this becomes plus. And then we have e to the negative t sine t dt, okay? Okay, then round 2. So before I forget, subscript 1, 1, 1, 1. And then u now is, and we have to stick with it, so e to the negative t. And then dv here is now sine t dt. Then differentiate this one, so you have negative e to the negative t dt. And this one now, this one becomes minus cosine ta. Y'all got that? Okay, and then what we have is this one from previous line. And we have uv, these two, so this one is minus e to the negative t and cosine t minus the integral of these two. So I have a minus sign, minus sign, minus sign. So I have minus e to the negative t sine t dt. Still with me? Y'all with me? My shoulder itches. Okay. And then, see, you see why I didn't want to do this limits of integration and carry it down, write it, bracket, bracket. That's a nightmare here. Okay? And then this thingy is equal, that thingy is equal to this whole thingy. So I like to add this thingy to the other side. So I say 2 of e to the negative t sine t, like therefore, dt is equal to this thingy. You wanna common factor e to the negative t? Yeah, sure. E to the negative t. And then we have sine t minus cosine t plus c. Now, instead of rewriting the line, we can just divide both sides by 2, eh? So take the eraser out and then boom. And then stick it right here. Good.
Do we have to rewrite it like that? Or like, can we just write the next step as 1/2 e to the negative, like all of it?
Yeah, I mean, I said if you do an eraser action or just wrote it, how am I going to know, right? As long as you have a right answer here, I'm going to assume you know what you're doing. Right? I mean, after it's done, like, did I have 2 here and then erase it or not? I mean, nobody will ever know. Right?
Do we have to write like the extra, like the other side of the equation, the like
Which
the
side?
therefore and the equal sign?
This side? This thingy?
Like like the 3 dots.
Oh, this?
Yeah.
No, you don't have to write this 3 dot, but you have to write this whole thing.
Okay.
Or you can have 2 here and not have 2 here, but when you plug it in here, you have to remember to put 1/2. Right? It's a judgment call, but I always do it here like this so that it's less prone to make that mistake. You know what I'm saying? Because I'm fact over here. You get it?
Okay, thanks.
You know what I'm saying, right? You cannot say that is equal to this or this. See, if you connect with the equal sign, this expression is not equal to this. God, no, that's mathematically incorrect. And whenever I see mathematically incorrect statement, I have to take a point. You know, well, in this case, more than 1 point.
Okay, got it. Thank you.
Yeah. Chiffon.
Oh, it's just minor things, but shouldn't that be e to negative t cosine t on the left side?
Which one?
The blue part shouldn't
Oh,
be.
this. Oh, it's not minor. Oh, it's a big deal. Yes, nice catch. This is, of course, cosine t. Right? What the hell? This is cosine t as well. Yeah, I'm so glad you caught it. This is cosine t. Right? Good. And then I caught myself this mistake. 2, 2, 2, 2. Okay, now it's perfect. Do you see any other mistake? Good. Now we are ready to come back here, like different stages. So this thingy is equal to 1/2 of this. So with pi, I'm going to start the bracket e to the negative t over, and then I'll put 2 pi here and open parenthesis, sine t minus cosine t. And then from 0 to, oh, 0 to 2 pi. Are you with me? And then you're thinking, wow, this is a nightmare. How are we going to evaluate this? Watch this. Whatever the heck this is, if I put 2 pi and if I put 0, these are periodical functions. Aren't these two things exactly the same thing as far as sine and cosine is concerned? I might as well have 0 to 0 here. You know what I'm saying? See, this gives you 0. This gives you 0. This gives you 1. This gives you 1. So they're going to cancel. So the whole thing is 0. How about that? And that makes sense because this is some kind of periodic function and you are integrating over exact same. Then half of the time is positive, half of the time is negative. Then they will cancel each other and give you 0, right? We could have predicted that from the beginning, but then, hey, where's the fun then, right? Such a beautiful problem, eh? Question before I move on to the most hideous integral ever. Well, up to whatever, probably this far. And probably this is the most hideous one, which is this. Okay, this one. See, this is going to be massive and I don't want to carry these things. So I'm going to just do the antiderivative first then, okay? Kind of like this thing, this side. So I'll do that first. Put this, fasten your seatbelt. Yes.
Mr. Kim, sorry for the last problem. I get that 2 pi and 0 are like basically the same, but other than the trig other than the trig part of the function, there's also the e to the negative t part. So wouldn't it not be 0?
Why don't I show you the whole thing?
Like it's e to the negative 2 pi and e to the 0.
Okay, let's do it.
Okay.
So this is e to the negative 2 pi over 2 pi, right?
Yeah.
Times negative 1, right?
Mm-hmm.
Because the 2 pi gives you 0 and this gives you 1 with a minus sign. Minus, oh, actually, I think you're right. E to the 0 over 2 pi. And then this thing gives you negative 1, huh? Whoa, 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 you are right. Oh my God, I'm so glad you caught this now, right? And they don't cancel. How about that, eh? This is a really good session. So this thingy is just negative. I'll just write negative. I think I'm gonna common factor 1 over 2 pi. And then, why am I common factoring like that? I'm gonna get rid of the negatives. Hold on. I'm gonna common factor 1 over 2 pi. And then I will have e to the negative e to the negative 2 pi. And plus, this thing is 1, right? Oh, nice catch. Very nice catch. Good. I was a little premature. I was too excited to cancel things out. Good. This will make a great video. Okay, now we do the most hideous one. As if that was not bad enough, right? Okay, so I'm going to do this thingy first. Secant cubed x dx. Now it's a judgment call to have a 2 in front now or later, but let's not, okay? Because you will see just this generic thing more in the future. So let me just do it this way, then later we'll put 2, okay? Now that thing is same as tangent squared. I'm not gonna skip a line because children get lost. So secant squared x times secant x dx. Remember this trick when you have an odd number of trig functions, right? And then secant squared is tangent squared plus 1a. 1 plus tangent squared, which way do you want to see it? Tangent squared plus 1, or is it 1 plus tangent squared? 1 plus tangent squared. So far, so good? Okay, then we have to separate this integral. There's no good way of doing it. So secant x dx plus this thingy of tangent squared. Did I put data here? My God, making so many mistakes today. Okay, now, do you remember what this was a few days ago in an example? We multiply secant x plus tangent x over secant x plus tangent x, that thingy? Or do you want me to do that on the side as well? I mean, I can do it again, we have time. Who wants to see it? Virtual hand? No? So this one at least is easy. This one is ln secant x plus tangent x. Not that we memorized it, but we just evaluated in our head, right? That thingy. Now, then this is like, oh, this is like side and then another side, right? Subside. Okay, change the color and then we'll do that part. So here is tangent square x secant x dx. And this is integration by parts. Which is u and which is dv is the question. We have to decide wisely. Somebody tell me what's u and what's dv. And we can go through a few of them. What was it? You're breaking up?
U is tangent x.
Tangent x is very good. This is tangent x. And rest of you who don't see it yet, will watch this. Tangent x, secant x dx. The key is, do we know how to integrate this thingy? Right? You have to put, for dv, you have to put something you know what the antiderivative, otherwise this scheme fails. And antiderivative of secant x tangent x happens to be secant x, isn't it? Yeah. How about that? You get it? Well, then what's du? Du is secant squared x. You with me? Say yes. Okay, so this thingy now is uv. This thingy, so we have secant x tangent x minus the integral of these two, secant cube. You with me? But then, wait a minute. Where have we seen that secant cubed x before? Here, right? What? That whole thing is in a loop? Yes, it is. So we come back here and we copy that down. So this is now additionally plus secant x tangent x minus integral of secant cubed x dx. Now, guess what happens? I'm going to add this thingy to that side. You get it? So, therefore, integral of 2 secant cubed x dx is equal to ln space, because I'm going to put 1/2 later, secant x plus tangent x plus secant x tangent x plus c. Oh my God. You know what I'm saying? Wait, we can divide both sides by 2, but I think our original problem had 2 here before, so let's not divide both sides by 2 then. I usually divide both sides by 2. You know what I'm saying? You want me to do it? Just to finish it up, just to see what this thing is? Yeah, let's do it. Oh, I'm going to do it like this. This time I'm going to make a copy and paste because this is a line we need. Do it like this. And then I'm going to erase that thingy and put 1/2 here. Okay? Now we are ready to go back and then shove it in here. I think I can put it in this space. Maybe. We'll try. You can move it around. So change the color again. Dang, this problem I told you is ugly. So therefore, 2 of from negative pi over 3 to 0 of secant cubed x dx is equal to our thingy here. This line. Ah, heck. Why don't I make a copy? It's a computer, right? I have that going in distance learning. And hopefully it'll let me change the color. Yes. Okay, that thingy. Bracket. What? This is so unstable screen. Bracket. And from negative pi over 3 to 0. Are you with me? Who's lost? Now is a good time to speak up. Good. Now evaluate. So plug in 0. If I put 0 here, that becomes ln 1. That looks ugly. I'll just say ln 1 because tangent 0 is 0. So I only have 1, which is 0, by the way, plus. If I plug in 0 here, this is 1 times 0, eh? You with me? Minus. Now I plug in negative pi over 3, so we have ln. What is secant of negative pi over 3? There. Oh, come on, people, trick. You want me to draw the triangle for you? Come on. Pull it together. What is secant of negative pi over 3?
2.
2. Thank you. 2. Positive 2, right? What is tangent of negative pi over 3? Oh boy. There.
Negative root 3.
Negative root 3. Okay. Thank you. Negative root 3. Close. We don't need that absolute value after all because 2 is bigger than root 3, but hey. And then plus. And then this is the same thing. This is 2 and this becomes negative root 3, right? So minus 2 root 3. Like that, eh? Say yes. Okay, to finish off, this whole thing is 0. They're all 0, so it's just this. To make it look pretty, 2 root 3 minus ln, and then 2 minus root 3. Oh my God. That was ugly now, wasn't it?
Yeah.
Yeah.
Do we multiply the whole thing by 2?
Okay, no, we don't. And the reason we don't do it is, remember this whole thing is equal to just one of this, right?
Oh,
Or
okay.
1/2, right? Okay. You know what I'm saying? Alrighty. any questions? That it?
Mr. Kim, can I see number 39 from the supplement?
Okay, so on top of this, we'll do 39 then, eh? Okay, let's see if I can quickly get that. 39. I should have it, and yes, I do have it. Oh, so this is a lot less ugly. Okay, let me make a copy of that. And then we're right on time. $39 is here. Okay, let's do 39. So it's a similar tactic now, isn't it? Okay, so let's find the antiderivative first, shall we? Okay, antiderivative first, because generally when you do this, you don't know how ugly it's going to get. You know what I'm saying? So let's do tangent, just the tangent. We'll multiply 4 later if we have to. Dx, and then you separate. So we have tangent squared x, tangent x. And you can skip this line if you want to. And what's the tangent square? That one is now secant squared x minus 1. And this is much nicer than the other one. So far so good. Now we separate this. So we have, let me write it like this, tangent x secant squared x dx minus, and the other one is just the tangent x, isn't it? Okay, tangent x dx. Okay, this one is u sub, isn't it? And this one is also u sub, which I'm going to do on the side now. Okay. So this one, I'm going to copy this. We'll do it right up here. And let's say red color. Okay. This one, my u is equal to tangent x, and then du is equal to secant squared x dx. You see, that's nice, isn't it? So this turns out to be just u du, eh? Which of course is u squared, therefore 1/2 plus c, and that is equal to 1/2, and u happens to be tangent x. So this is tangent squared x plus c. You get it? I'm going to write that in. So this is 1/2 tangent squared, or equal sign, x. And then I'm going to figure out this second one. Okay? Okay, second one, running out of space. I'm going to do it bottom. I'm going to do that with blue color. So this thingy is a sine x over cosine x, eh? And this time u is equal to cosine x, and then du is equal to negative sine x dx, because when in doubt, you're supposed to go with the denominator. So this thingy becomes negative sine here, and then du over u, eh? Which is negative ln u plus c, and that becomes negative ln, and then, oh, absolute value, cosine x. You with me? So plug it in now. Do you see this? We picked up minus sign, and there's a minus sign there. I mean, we could have put minus sign here, but I decided not to. So we have to be careful, though. So this becomes plus now, and then ln, and then cosine x, close, plus c. So far so good. Now,
Why didn't you put the plus c from the 1/2 tangent squared x?
E is there, but then I have to combine the like C and a D, but then the constants combine, so I just put it as one constant. How about that? Okay, this C is different than this C. You know what I'm saying? And they kind of add and still give you C. How's that?
Okay, thanks.
Technically, I should have put C here, D here, and E here. How about that? You want me to do that? I mean, I can totally do that. Nay? No, that's too picky. Yeah, let's not scare children, because some children will say, do you have to do that on the test? No, you don't. Okay, now we are ready to evaluate from 0 to pi over 4, okay? So finally come back to, so 4, and then 0 to pi over 4 of our original tangent cubed x dx will turn out to be, okay, do I want to keep this for distribute? Nah, I'll just keep it outside. And then we have 1/2 tangent squared x plus ln and cosine of x, and then from 0 to pi over 4. So far so good? Okay, that's 4, and let's plug in pi over 4. What's tangent pi over 4, people? What time's running out? Okay, I'm gonna have to do it 1. And then cosine pi over 4 is?
Root 2 over 2.
Root 2 over 2. 1 over root 2. I'll just do it this way. Okay, minus, and then 0. Tangent of 0 is 0. Cosine of 0 is 1. Ln 1 is 0. So that is it. You get it? And that is equal to 2 distributing plus 2 ln 2. What? Too much algebra? Think about it.